All right, everyone. My name is Ryan Schul. Welcome to my channel. This is all about data science, machine learning, deep learning, artificial intelligence, finance, and some other topics that I think you will find very practical and very useful too. So, if you know me at all, if you've seen some of my other videos, you know that I love predictive analytics. I'm going to get out of my comfort zone a little bit today and teach a lesson on natural language processing. And this is going to be fairly comprehensive. There's a lot of topics that we can talk about in this um, main topic. There's a lot of subtopics. So it's going to be pretty comprehensive, but we might not touch on every single nuance of natural language processing. So forgive me in advance if we don't get to it. There's some of the time and limited resources. I don't think you want to sit through a 12-hour video anyway. So I'm going to try to condense this into about 25 or 30 minutes. Let's see how it goes. Okay, so natural language processing is essentially a way to understand things that helps us bridge between human language and computers, right? And essentially, it enables machines to understand, interpret, and generate human-like interactions that are most meaningful and useful. Okay, so NLP is very practical for many reasons, including processing and analyzing large volumes of text, improving human machine readable interactions, automating repetitive language based tasks, extracting meaning and insights from data, enhancing accessibility, personalizing, and recommending different topics or different resources for people, supporting critical applications, multilingual communication, right? Like translating from English to French or French to English or any language to any other language, enhancing search and information retrieval. And basically, language is a core component of human intelligence. That's why we study NLP, okay? So there's a lot of real world applications for natural language processing, including healthcare, extracting critical information from medical records, and, as well as business, analyzing customer feedback and automating customer support, chatbots, things like this, right? Educating and building intelligent tutorial systems, social media marketing, monitoring, trend analysis, detecting fake news, and so on and so forth. Okay, so I decided to focus on this thing for this lesson. This is National Park Service, Glacier National Park. So this was my inspiration for this NLP lesson right here. I love Glacier National Park. I've been there a couple of times. Absolutely phenomenal place to visit. I would highly recommend it. So there's a couple things in this webpage that we're going to screen scrape and work with. Mountains, basically, you can't go there without talking about mountains. What's the continental divide? That divides water flowing into the eastern region of the United States, which eventually flows into the Atlantic Ocean and the western part of the United States. So it flows to the Pacific Ocean. The Triple Divide Peak is the one peak which is very unique the in the United States. It might be the only in the United States, not the only in North America, I think. But it's where the mountain is so tall, any runoff from any rain will flow into one of three water basins, either the Atlantic Ocean, the Arctic Ocean, or the Pacific Ocean. Okay, that's enough about that. That's Glacier National Park. So when we download this information, what can we do with it? I'm going to create a response. Okay, this is just a web tool that go ahead and does a fetch of all the data on that site. If the response code is 200, that means it's successful. It goes ahead and executes the response and pulls everything into beautiful soup. Okay, and then we process that, and it looks like this. It's the first 500 characters from that website. Okay, I'm saying get everything 500 characters. Scrape text, Mountain Glacier National Park, skip to global NPS navigation, and skip to this park navigation. Okay, so I think we have a couple skip things over here. Skip, where is it over here? It's SKRP. Not seeing it, but it says that there's 5 of them there. Oh, anyway, so it's pulling in the data from that website, the language from that website. Okay, so we're going to do a few things here. We're going to tokenize the words. This is breaking down the words into pieces that are known as tokens. This makes it easier for the computer to work with these bits and bytes of information. These are called tokens. Okay, tokenization is important because this is the first step to creating a format where we can conduct natural language processing, okay, because it converts all raw text into pieces that can be analyzed, processed, and modeled by the computer, okay? So if we go ahead and tokenize the words, we get this right here. Here's the first 500 characters, again, like we saw before. So if you look closely, we have the page text right here, Control C, Control F. If I look for page text, we feed that down here. Word tokenize, we're tokenizing everything. Okay, you see that? And then we're taking the first 500 tokens, and everything essentially is just surrounded by quotation marks and separated by a comma. That's literally all it's doing, taking everything and converting it into bite-sized elements that the computer can interpret. Okay, so the next thing we're going to do after tokenizing all the words is clean and normalize the words. So we convert everything to lower text, remove stop words. So anything that's a stop word is words like the, and, I, um, anything that doesn't add a lot of meaning or purpose to the language is going to be removed, right? So if you have a lot of I's and me's and you and the word and, obviously and, so it doesn't add a lot of meaning or context to the um, syntax that we're trying to analyze here. So we just remove these stop words. Otherwise, we're going to have a whole bunch of words that really don't add a lot of context, right, or meaning to the overall um, body of language or corpus of language that we're dealing with here. Okay, so we remove punctuation. So any exclamation, period, commas. These are not important to understanding the meaning of the word. We're going to take the stems of the word. So the stem basically is the beginning of the word. So run is the base for running. Running, ran, has run, is running, all mean run, right? It's the same thing. You take the stem of the word run. Lemmatization is when you take the part of the word and convert it into a word where it's not necessarily just the stem of the word, but that does add a little more meaning, purpose, and context to the paragraph or to the phrase that's being mentioned or that's being analyzed here. Okay, so mountain has no base word or no root word, no stem word. Glacier, national park, U.S. Has no root word, right? So these stay here, but anything that's exciting can become excite. Anything that's running can become run. But with limitation down here, it's more like a linguistic rule that we follow to understand the parts of speech. So the actual word is reduced to the grammatically correct word, making it more accurate. So again, running, runs, run, better, good, context aware is important, right? We want to understand the context of the word. So this is a little bit more volatile, a little bit more sophisticated. Stemming is just taking running and convert it to run, right? So these three words, running, runs, runner, is all run. Studied, study is all study, right? It's all the same thing, but lemmatization, running, runs, and run are really three different things, right? Run is present, runs is present, running is present, but it kind of means slightly different things, right? In the stemming word, it's all reduced to one word, run. And lemmatization, running, runs, and run could be three different things depending on the meaning of the word. So it looks at words around the word that's being lemmatized too, okay? So now we're going to look at frequency analysis just to go ahead and plot the frequency counts of different words to understand how often this shows up, right? So I created lemmatized tokens. I'm going to work with this as opposed to stemming because, again, stemming takes everything that's the main word and reduces it to a subword or a part of a word. Lemmatization takes the context of the words, right? So if the context is meaningful, it keeps that context based on what's to the left of the word and what's to the right of the word, right? So here we have stemming, but also slower. When you're lemmatizing that, it's probably to keep everything, right? If you're stemming, it's just going to take stem and that's it. And it's not going to care about these words over here. So I think lemmatization is a better overall, more fuller, comprehensive view of the body of text here. So we're going to work with that. And I'm going to create a little function here and use a plotly chart to go ahead and look at the top 20 words, okay? And then the bottom 20 words. So the most frequently counted words over here, you can see park shows up 25 times, glacier 22, mountain 20, right? That's pretty obvious. Some of these show up just once. Vulnerability disclaimer, that looks like a zip code and phone number that just shows up once, right? So you can easily see what is more popular here. Park, mountain, glacier, national park shows up 11 times, mountain shows up 20 times. And these are the bottom least frequent words. USA, act, fear, index, stay, experience, things like that, right? So now, just by looking at this view, we see which words are more common and which words are least common. So let's take a look at part of speech tagging. This basically helps us understand nouns, verbs, adjectives, things like this, to create a full sentence with rich, full meaning, right? So it helps us understand the role of each word in the context of the oral sentence. We have to understand the text and any kind of aiding or enablement in the syntax of the overall semantic analysis that we're doing, right? Okay, so let's take a look at this. We're getting nouns, and is noun. JJ, I think, is adjective, right? National is an adjective, so it describes a park. Glacier describes um, the thing that we're looking at, right? Like packed ice. Park is a noun. U.S. is an adjective. National adjective. So it's taking everything and breaking it down into nouns, plural, verbs, verb past tense or base tense, adjectives, things like that. Okay, so we can go ahead and create a count or plot part of speech. So most of the things in this corpus of text are nouns. We have some adjectives and some CDs. I forgot what that is, and then and verb past tense and verb present tense. I think that's what it is. So most of the things here are objects, right? By and far, at least more than half of these objects are nouns. Okay, so we have a good understanding over here the frequencies of words, right? Which words show up less frequently. These show up just one time in the whole body of text, and then what's a noun, an adjective, a verb, an adverb, and things like that. So named entity recognition helps us understand named entities that are predefined. Like a person can be an individual, a location can be a geographical entity, country, city, organization can be an institute, an enterprise, a company, a corporation. A date is a date, and so on and so forth, right? So we're going to understand these and then again create a plot. Okay, so here's the counts of plots, and frequency is 4, 2 to 2. You see kind of a plateau over here that drops down to 1. These are the frequencies of these named entity recognition objects. Okay, so let's move on now to sentiment analysis. We can measure the polarity and subjectivity for every single sentence in the corpus of text. So you can do this for every word. I'm going to do it at the level of the sentence, so it has a little bit more meaning. If you do every word, you can take it out of the context of the sentence. I want to keep it in the context of the sentence and analyze the polarity or the subjectivity of the sentence. Okay, so when you run this, you'll see there's a sentence separated by the colon there. So Mountain Glacier National Park is a national park, so on and so forth. Explore National Park Service by exiting nationalpark.gov. That's the website, right? So polarity is 0.133 and subjectivity is 0.34. Over here, next sentence, dismiss all our alerts, contact between National Park Service. Then you have NPS photo. That's a short sentence there. Skipping down here, these mountains are also home to the heartbeat of 3 different river systems. Okay, that's what I said before, the parsing of the water going to the Arctic Ocean, the Atlantic Ocean, and the Pacific Ocean. So that's pretty cool. Of course, I'm going to mention that. That's unique to the park. And this page navigates to the middle fork of the Flathead River, follows the southern boundary of the park. So that's not polarity or subjectivity. It's just facts. Here's more facts, okay? And down, okay, so we get a little polarity and subjectivity down here. Glacier is home to unusual triple divide. That's what we said before. There are 3 drainages that come together at a single point. So that makes the park very unique. So that's pretty interesting. That has some polarity measurement and some subjectivity metrics applied to that too. So if we skip down here, we'll see it continues on and on. So we can overall understand like the meaning, the context, and the purpose of all this text that we're analyzing. So now we get down to n-grams, and n-gram, n is just being a number, 1, 2, 3, 4, 5, 6. N is whatever number you get it, you let it be. And we can look at bigrams, trigrams, or quadgrams. And this is where words occur most frequently counted together either 2 times, 3 times, or 4 times. So bigrams is 2, trigrams is 3, and 4 is quadrigrams. So these 2 words show up together 15 times. The park shows up 12, 9 times for comma and national park shows up 8 times. Glacier with apostrophe S, I guess it counted those as 2 words. Kind of looks like 1 to me, that counted as 2, that's fine. And then frequency to the shows up 6 times, okay? Trigrams only shows up 1 time of the park. So that was frequently, came up 5 times. There was nothing else. And for quadrigrams, we have NPS photo. East side of shows up 3 times. East side of the, east side of the, the A set. Okay, it's 4, 4. So it's all recurring patterns of 4 words consecutive and how many times that pattern shows up. Okay, so that can be useful too to understand. If you just look at this one graph, you can understand kind of the context of that whole body of text, right? The states in the national park system, into the Columbia River drainage, Pacific Ocean, period, and so on and so forth, right? So bigrams show 20 topmost word pairs. Trigrams show triplets and their frequencies, and quadruplets and their frequency. So n-grams are good for understanding the context and detecting patterns within the body of text, right? So single words are unigrams, and any kind of pattern recognition can come up pretty quickly when you're looking at n-grams from this perspective, right? Like what words show up as code words over and over. I guess there's only one occurrence of this, of the park, and then quadruplets are down here. Okay, so let's move on. The text vectorization methodology includes the analysis of the following, right? BOW is bag of words, TF-IDF is term frequency, inverse document frequency, and we can plot the most common bag of words. Okay, so like we're doing before, we count frequencies. We are going to do some manipulation on the text, some parsing, and chunking of the words to get everything into a format that's easy to analyze and easy to plot. Okay, so the 20 most frequent bag of words is park, that shows up 22 times, mountains, glaciers, and these are bag of words, right? So this frequency shows up over and over multiple times. Frequency, 14, glaciers, National Park Service, and divide, National Divide. The vectorization or visualization of TF-IDF is term frequency, inverse document frequency. So term frequency is how frequent do these terms show up together, and inverse document frequency says how many times does this word show up in this document given all the other documents too. So if you have like 10 documents and the word apple shows up many times in one, but not in the other 9, then one document that has apple multiple times is going to be focused mostly on apples, and the other 9 have basically nothing to do with apples. So that's the inverse document frequency concept, right? So we go down here, again, we can plot everything and get everything vectorized and chunked into word vectors to make this easier to work with. You can see the TF-IDF top 20 words is park. Shows up about 55% of the time, glacier 44% of the time, mountains 34, and so on and so forth. NPS divide, river, national years, down and down until the end. And then we can do word embeddings and visualization of these words and plot this on the 2-dimensional space. So you can see based on the dimensions of these words where all these words plot on this X and Y axis, X being the horizontal and Y being the vertical, right? So these are all the words here. And you can kind of tell like the similarity of words based on the plotting to what words go together, right? So if we go over here, plates, they're talking about tectonic plates, single valleys. Okay, so these words go together. And if you go down here to the southeast quadrants, we have shroud, drainage, water, ecosystem, clouds, glacier, continental divide, okay, and so on and so forth. So that is term frequency, inverse document frequency, and word embeddings, and then visualizing those embedding elements on the XY graph. So now we can go ahead and do clustering and topic modeling. The concept here is known as latent Dietrich allocation, LDA, for topic modeling. And an example of LDA is given to us right here. We can take out any stop words and punct. We download the Natural Language Toolkit resources to go ahead and help us with this. We are taking out any kind of what is this? Oh, lowercase, convert all text to lowercase, so we can compare I's to I's, like capital I and small I are going to be the same. If they weren't lowercase, they would be treated differently, but anything that's uppercase or lowercase is going to have the same context and same meaning, so we don't want to make the computer confused or make the algorithm take a long time to converge to create its final analysis and present the results. We want to converge pretty quickly, so we make everything lower and tokenize all the words to help the computer to do its task quickly and easily. When you go ahead and run this, you'll get this output right here, which is pretty cool. You'll have the different topics right here. Starting with 1, it goes up to 4, and when you highlight on each of these distance mapping objects right here, you could click on topic 1 and you can see all the details of the topic. So we have NPS, photo, river, park, divide, range, glacier peak, so on and so forth. When we click on the next topic, we have this: park, national skip, mountains, glacier, NPS. Here's number 3, topic number 3, divide, years, glacier, national park. Here's 4, mountains, glaciers, rocks. So it breaks everything into unigrams like we saw before, and these are the main topics based on the counts of the circle, or counts of frequency of the circle is relative to the size of the circle, right? So you can go to a previous topic like this, or next topic. You can click through these at the top, and then you can also set the adjacent relevance metric by adjusting this guy over here, right? So pretty interactive, pretty cool what you can do with this based on the topics, and then all the breakdowns of all those topics, right? There's not a lot of relevance, but if you shoot this up to the max, then you get all the relevance, all the words relevant to each of these topics right here. So it's LDA analysis, latent Dietrich analysis. So that's pretty cool. You can play around with that and get some more insight into the body of text that you're working with. Here's the top 10 words, right? So topic 0 right here, these are basically clusters of words. Although I don't know if it's actually clustering these together per se. You can certainly cluster words together. I think the approach here is Genesee Biz. I think the approach is similar to clustering. I don't think it's doing clustering per se, but it is another experiment that we can run on the text to cluster words that are similar together, or even sentences that are similar, right? So there's a couple other types of analysis we can do. I have another video about that. I didn't do that specifically in this video. It's just too much to cover, but that's another thing to consider. If you did want to create clusters of words, you can do individual words clustered together or entire sentences clustered together, either one, right? So LDA helps us to understand different topics, right? So topic discovery, document classification, we saw that, right? Based on different topics that we analyze, information retrieval, and then recommendation systems. So pretty cool. Here's one more item to cover: topic modeling. So here we have the first topic, just like we saw in LDA. Here's topic number 1, 2, 3, 4, 5, okay, and so forth, and so on and so forth. So that's a little bit more interactive. Here is a very similar concept, just different execution. We have topic 1 and then the frequency of words. If I click on this, I think you can see everything together. Yeah, so here's topic 1, mountains, glaciers, many, rocks, feet, learn, sedimentary, and then word weights. So the overall contribution is going to add up to 100%. You can see mountains is most frequent, glacier, many, rocks, so on and so forth. Here's topic 2, 3, 4, and 5, right? So the top 5 topics, and then the weights, or the percentage of each of these words showing up in the overall relative weight for the entire topic, right? Being when you sum these together, it adds up to 100%. So we can also build NLP models, right, where we have X variables and Y variables. So I get into this pretty extensively in my other videos. So this is a machine learning approach to pick independent variables. That's your X variable, and the Y would be the predictive variable or the target variable, right? So here's the Y train, Y test. So those would be dependent, and these are the independent, right? We did a train test split right here. Okay, pretty standard machine learning. And this is the classification report. This model uses a phase classification to create a classification report and provides metrics to evaluate the model's overall performance, right? So the performance is pretty decent here. We get 100%. Park info 1.0, 1.0, 1.0, all over the place, right? But you have to consider too, this is not a huge body of text. This is a source. It's a few paragraphs of words. So it's not unusual or not not surprising at all that you're getting 100% in terms of precision recall and F1 score, because the body of text is pretty small. So although it looks good, it's like I would take that with a grain of salt, because it's just a small body of text. We're not doing like massive volumes of text and doing classification on that. It's a very small body of text, so the model can cut through it pretty quickly and easily, right? So moving on, summarizing the entire body of text, we can summarize everything. Use a parser, summarizer, return all the sentences in the body of text for a summary. So here we are summarizing what is in this whole body of text. Again, it's not huge, right? So it's going to run pretty fast and pretty efficient. If you did have a huge body of text, like hundreds of pages here or thousands of pages, it would still cut through it, but it would take a lot longer to do the job, right? This one finished up pretty quick. It's pretty straightforward and pretty simple. Aptly named waters in each side of the mountains start their journey. and flow through three different oceans, right? So that's the triple, what was that called? The triple peak? Triple peak. No, that's something else. Oh, I guess tri-peak, triple peak. And anyways, we saw that over here. Triple divide. Okay, so I think that's what this thing is talking about. Whoops. Wait, I go down a bit. Sorry. Got off of the tangent there. Three different oceans. So the triple peak goes to three different oceans. It's giving us a summary of the whole body of text, wide variations in elevation, and they're talking about paths and highway to land sculpted and carved by glacial geology. Okay, so here's another approach at summarizing a text. This is using plain text parser, tokenizer, and LSA summarizer. So there's many ways to skin the cat. We can use a counter and then summarize with keywords. So this is another approach to create a summary of the body of text. Skip to global MPS services, and it's talking about all MPS open menu, close menu, explore this park, and the Great Divide runs through Glacier National Park. Okay, so one more way to summarize the text is to use spaCy and Pi text rank. Again, different means to the same end. Three mountain ranges border or cross Glacier National Park. It's talking about search sites on MPS, close menu, explore park, explore National Park Service, and so on and so forth. So it's trying to attempt to summarize this whole body of text into a couple of sentences, right? 2 or 3 sentences. So we can also do language predicting or predict the next word in a sequence of words. Okay, so for any LLM, this is exactly how an LLM works. I mean, they have other functionalities too, including transformers. We're not using a transformer here, but we just use a simple GPT tokenizer to encode and then make predictions about what the body of text is going to be in the sequence. So if I say Glacier National Park is known for its, that's the input right here. If I do Control F, input text goes here, and we are going to return tensors using probably some type of TensorFlow, I think is built into this, or at least a tokenizer. These are the input IDs. This floats down here to the model, and the model will generate the output based on the input IDs. Maximum length is 50. Maximum sentences, no repeat n-grams, top K token. So these are all the parameters you can add. If you leave it blank, it's going to kind of go wild, right? If you don't add a constraint or a parameter here, if you add a parameter, then it's limited to 50 characters. And it says, based on this input text, Glacier National Park is known for its its amazing views of Lake Ontario, which provides beautiful backdrop for the spring and summer. Okay, so that is it. We did a lot here. We covered a lot of NLP topics, certainly not everything. It's not comprehensive, not mutually exhaustive, but I think this is a great overview for NLP and a lot of things you could do. So to make this adaptable for whatever you're doing, you can go ahead and put in any HTML site that you're looking for, any website. It can be news, it can be sports, whatever you want. National parks, I like national parks. Put in national parks, and you and I can be good friends. That's it. So you put in this variable here, and everything else should flow down. So it's pretty dynamic, pretty scalable, up and out in terms of what this thing can do. And I think, if you spend a little time with this and roll up your sleeves and get down into the code, explore, make some changes, make some improvements, whatever. And I think you're going to learn a ton about this. Okay, so I think that's it. I'm trying to get down to the bottom. It's jumping off the thing. I mean, why couldn't it not go down? Okay, there, finally. It was way too hard. Okay, so that's it. Thanks for your full undivided attention today, guys. I'm going to wrap it up here, and I will see you in the next one. Take care. Bye.